Hey guys, today we're going to be discussing the concept of partial pressures. Now, partial pressures is predicated on the idea that every gas acts independently of any other gas. And what that means is each gas exerts its own independent pressure. Partial pressures add together to give you the total pressure of a container. So this means that if you look at a container that has multiple gases in it, the total pressure of that container is the sum of each of the partial pressures of the gases in that container. So what we're going to do today is we're going to explore this idea and we're going to do some practice problems to see how it works mathematically. So let's look at a particle diagram that represents what I'm talking about when I'm talking about partial pressures. Below, you see three separate containers, one with nitrogen, one with hydrogen, and one with oxygen in it. And above, you see that I've taken these three separate containers down below and I've simply combined them into one. Well, let's for a second look at those bottom containers. In the bottom left container, the nitrogen exerts a pressure of 2 atmospheres. The hydrogen 3 atmospheres and the oxygen 3 atmospheres in each of their own respective containers. But let's now think for a second if these weren't 3 separate containers. What if they were one container with 3 separate gases in it? Even with all gases combined, each individual gas is still going to exert the same pressure it did beforehand. So the nitrogen in the overall container above still exerts only 2 atmospheres of pressure. The hydrogen and the oxygen each are only going to exert the 3 atmospheres as they did below. So what's changed in the container above is not the partial pressures, but the total pressure. The total pressure in the container above is represented by the sum of all of the partial pressures down below. 2 plus 3 plus 3 gives us a total pressure of 8 atmospheres in the above container. But each of those individual gases, remember, are independent. They exert their own partial pressures. They just simply get added together. So they're not going to impact each other. They're simply summed to give you the total pressure. Now, in terms of partial pressures, what we're seeing is normally we're in the same container, which means temperature and volume are going to be constant. What's going to change is the number of moles. So when we're looking at partial pressures, we have to account for number of moles of a gas, and the calculation of a partial pressure can still be PV equals nRT for any gas independently. Or if we're looking at the total pressure of a gas, then all we have to do is take the number of moles of each of our individual gases and add them together, because the total pressure would be represented by the total number of moles. So in this diagram, pressure of nitrogen would be PV equals nRT, where N represents the number of moles of nitrogen. For hydrogen, PV equals nRT, where N represents the number of moles of hydrogen, and for oxygen, PV equals nRT, where N represents the moles of oxygen. So let's do a practice problem where we're going to see mathematically how to calculate partial pressure if we're given, say, the total pressure and the number of moles of each gas. So here I've got a sample with 2 moles of hydrogen and 1 mole of nitrogen. Now, I see that this entire container has a pressure of 9 atmospheres. And as a result, what I know is that the nitrogen and the hydrogen are going to contribute to that total pressure, because those are the 2 gases present. The question is, how much do they contribute? Well, PV equals nRT, which means that the partial pressure is relative to the number of moles. So if we look at number of moles, hydrogen makes up 2/3 of the total number of moles, which means it also makes up 2/3 of the total pressure. Nitrogen makes up 1/3 of the total number of moles, which means it makes up 1/3 of the total pressure. What that tells me is that the hydrogen would have a partial pressure of 6 atmospheres, and the nitrogen would have a partial pressure of 3 atmospheres. Those 2 partial pressures add up to 9, which is the total pressure that I've seen in the container. Now let's take a look at a slightly different type of practice problem. In this one, we're still going to be given the amount of each gas, but we're going to give it in grams this time. So what I have here is 11 grams of hydrogen, 210 grams of nitrogen, and 96 grams of oxygen. Each of these is going to be in the same container, and therefore, each of them is going to exert their own independent partial pressure. We need to figure out how many moles of each there are first. Then what we can do is calculate their partial pressures. So here's what we're going to do. We're going to start by dividing each number of grams by the number of grams per mole for that gas. So for hydrogen, molar mass is 2 grams per mole, so it's 11 divided by 2, which gives us a number of moles of 5.5 moles of hydrogen. For nitrogen, we have 210 grams of nitrogen, which weighs 28 grams per mole, remember N2, and therefore we have a total number of moles of nitrogen as 7.5 moles. All right, so we've got 5.5 moles of hydrogen, we've got 7.5 moles of nitrogen, and for oxygen, we take our value of 96 and divide it by the molar mass of oxygen, which is 32 grams per mole. Remember, it's O2. And we get a total number of moles for oxygen of 3. So we have 3 moles of oxygen. This means that we have 5.5 moles of hydrogen, 7.5 moles of nitrogen, and 3 moles of oxygen. That means we have a total of 16 moles of gas. So we have 16 moles of gas present. Each of those gases is going to be assumed, again, the ideal gas law, to have the exact same effect on the pressure. So each pressure exerted is going to be relative to the mole fraction. So if the total pressure of our container is stated as 3,800 torr, that means the pressure exerted by each gas is equivalent to its mole fraction times that number, which means if we have 16 total moles of gas, what we're going to do is initially multiply the mole fraction of each one. So for hydrogen, it would be 5.5 divided by 16 times 3,800 torr. Additionally, what we could do is if you wanted the answer in atmospheres, we could convert first from torr to atmospheres. This way, what we're doing is only one conversion of atmospheres as opposed to multiple if we were to have to do it 3 separate times later. So let's go ahead and convert from torr to atmospheres. 3,800 torr divided by 760 torr per atmosphere gives us a total of 5 atmospheres. So we have 5 atmospheres of pressure present, which means we're going to take our mole fractions and multiply by that total number of atmospheres. So 5.5 divided by 16 times 5 represents the partial pressure of hydrogen. This number is 1.72 atmospheres exerted by the hydrogen molecules present in this container. All right, so for nitrogen, what we're going to do is 7.5 divided by 16 times 5, and that value is going to be 2.34 atmospheres. And finally for oxygen, now we could do one of 2 ways. Either we take the partial pressures of nitrogen and of hydrogen and we add them together, and then subtract that pressure from the total, all right? So 5 minus the pressure of hydrogen minus the pressure of nitrogen. Or we take the mole fraction of oxygen, which is 3 over 16, multiply it by the 5 atmospheres of total pressure. We get a partial pressure of oxygen of 0.938. So in this circumstance, we found all 3 partial pressures. They're relative to the total number of moles and the mole fraction of each of the 3 different gases. Remember, each gas is independent of each other, which means we can make some assumptions as to how much pressure they exert. This is only true because of their ideal nature. Let's look at the second practice problem. In this practice problem, it's similar, but we're going in a different direction. I'm given the partial pressures of 3 different gases, and using these, I need to figure out the mole fraction of just the carbon dioxide. So I've got the pressure of helium is 5 atmospheres, pressure of carbon dioxide is 11 atmospheres, and the pressure of my neon is 6 atmospheres. So here are my 3 different gases. That means that if I'm looking for the mole fraction of carbon dioxide, I need to figure out what percentage of the total pressure is made up by carbon dioxide. Well, total pressure is going to be the sum of the partial pressures. So I take my partial pressures, I add them together, I get a total pressure of 22 atmospheres. Carbon dioxide makes up 11 of those, which means it makes up half the total pressure. That means the mole fraction is also half. So in other words, carbon dioxide exerts half the total pressure, therefore it exists as half the total number of moles. All right, now we're going to do a practice problem that's really kind of challenging. So what I'm going to have you do is read the practice problem, pause the video. When you're done, or if you get stuck, unpause the video. When you come back, we'll work through it together. So the challenge in this problem is this is not simply an ideal gas law type problem. It's actually a combined gas law type problem. Remember, before and after. So we're manipulating something about this problem and we're changing different aspects of it. But the nice thing is, if we double the pressure total, we're also doubling the pressure of each individual gas in the container because of the fact that each pressure is independent of each other. That's great because we can just apply that idea of independent partial pressures to the combined gas law we've already learned. So we're going to look at each gas independently. Let's start with the nitrogen. Now the nitrogen starts with a pressure of 4.75 atmospheres in a 1 liter container at 26 Celsius. It's then moved into a new container. That new container is at 20 Celsius and has a volume of 10 liters. What we can do is, again, apply our combined gas law. P1 times V1 over T1 equals P2 times V2 over T2. Remember, the number of moles didn't change, right? It was going from one container to the other, so the number of moles canceled, all right? Now we're solving for the final pressure. The final pressure of nitrogen, when we plug everything in and solve, is 0.465 atmospheres. So that's the new pressure of nitrogen alone. We're going to do the same thing for the oxygen. So again, we're going to start with our P1 V1 over T1 is equal to P2 V2 over T2 for the oxygen. Oxygen starts in a container at 5.25 atmospheres, and that container was at a temperature of 26 degrees Celsius. The oxygen container was originally a volume of 5 liters. So now what we're going to do is we're going to take that oxygen and put it in the same container that we had already put the other gas. But, again, they're independent. So we're going to just treat the oxygen as if it's in a new empty container. So our new volume is 10 liters. Our new temperature is 20 Celsius. Remember, in all temperatures, and I forgot to mention this in the last one, but remember, in all temperatures, we need to convert to Kelvin. So remember, we're plugging in Kelvin temperature values here, not Celsius temperature values. So what we're doing in the end is finding the partial pressure of oxygen by plugging in P1 V1 over T1 is equal to P2 V2 over T2, solving for P2, and the pressure of oxygen becomes 2.57 atmospheres. Okay, so now we have found the pressure of the nitrogen and the pressure of the oxygen in the new container. So we simply add these two together to give us the total pressure in our container, and that's going to be 3.04 atmospheres. This is a tricky problem, but it really does connect the idea that when we're dealing with partial pressures, they are independent of each other and can just be added together to give us a total pressure. All right, so that wraps up today's video. Let's do a quick recap. Today we talked about how to find and use partial pressures of different gases. Remember, partial pressures represent independent pressures of each individual gas in a container. We can do this because the gases we assume to behave in an ideal way. Now, we can convert into partial pressures using mole fraction or use mole fraction to find partial pressures. And in each circumstance, it's just going to be a proportion like we did with our combined gas law. I'd like to thank Graham Bayer and Sean Lendrum for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.